So please, let's not fight for volume, all right? So we do have a quiz coming up on a mid-unit momentum and impulse quiz on Thursday. And so make sure you're practicing, paying attention. And so we got today and tomorrow to prep ourselves. I did post in Canvas a couple of practice quizzes. However, it's for all momentum and impulse. And so really the only thing left is center of mass and then the math behind two-dimension conservation, okay? We've covered all the big topics, and so you won't see a lot of stuff added after the quiz on Thursday. It's just continued practice, higher level questions, all right? So we'll mainly be focusing on center of mass for a couple days and then the NIMSY AP level free response questions, all right? And so don't feel you have to do both of those concept quizzes. If you come across one that's like, whoa, I haven't done the two-dimension math yet, then just know it's probably going to be saved for the end of unit exam. Okay, hold on. Okay, so let's try number 10 at the top. We got a large ball of mass 2m and a small ball 1m. They're moving with equal speeds of v. Okay, so your lowercase v is kind of the generic speed, and then they're saying, hey, it's a capital V. They collide head on in a perfectly inelastic collision. What does perfectly inelastic mean? They stick together. And so that's a common description of the collision, but what does the physics mean? Okay, energy is not conserved, so KE specifically is not conserved, but what is? Momentum is conserved. Okay, unless they start talking about external forces on the system that are changing the momentum, external forces doing impulse on the system, which they don't mention, okay? Most of your collisions, yes, momentum is going to be conserved. Which of the following are possible after the head-on collision? And so we've got, do they stop moving? Is it V? Do they not change? Is it V over 2? Is it 2V? Or none of these? And so what do y'all think? A? B? None of these. Not because, oh, it's none of these is present, so it must be that. But let's do the physics behind it. What would the velocity be after the collision? And so going with that momentum conservation, net momentum initially before the collision is going to be equal to the net momentum after the collision. Well, both of them are moving at the same speed. However, if it's a head-on collision, what does your picture look like? Maybe 2m is moving to the right. And so maybe little m or 1m is moving at the same speed, but momentum cares about direction. So its velocity would be negative v. And then head on, just like a car wreck, unfortunately, they're just going to hit each other straight on, no angles. Okay, angles are coming later, but no angles with a head-on collision. But after the collision, they're going to stick together. And so in our conservation statement, we would say 2m times a positive v plus a single m and a negative v equals, well, if they stick together, what's your system mass? 3m. And here's the final velocity that we're trying to solve for. And so on the left-hand side, I get 2mv minus 1mv. What remains on the left? 1mv equals 3m VF is what we're looking for. What do you notice? The variable m cancels, the factors stay, but m variable cancels. And so to solve for v, f, it would be the original speed given divided by 3, which is none of those. And so none of these are possible. Make sense? Okay. Now, I think y'all started the next question, but I actually need a video for this one. I thought my previous recording included it, but humor me while we start this one over, okay? And so you have an advantage. You've read it, seen it, talked about it before, but I heard you didn't finish this one. Okay, so complex, higher level. And so you'll see why in just a second. This is in the higher level. 2 billiard balls, equal mass, yay. They have a perfectly elastic. Now you're like, Miss Earhart, you didn't put that in the table, perfectly elastic. Y'all, there is only one elastic, true elastic. It's just one. Right, right. So elastic does tell us something. Yes, we're going to have a bounce off. However, that's not the only thing that describes an elastic collision. You can have partially inelastic bounce off, like a baseball and a bat. So what else does elastic mean? Kinetic energy is conserved and momentum. Okay, so we've got both conserved. And it's another head-on collision, which just tells us no angles. And so if you want to draw a picture, maybe ball 1 is moving to the right, and later they tell us one of them is going to be going 2 meters per second. And then the other ball, equal mass, head on, it's straight away, right? I'll call that ball 2, is going 3 meters per second. And then they're going to collide. Yes, they're going to bounce off. And with this head-on, no angles, ball 1 is going to end up probably going what direction? To the left. At its final velocity, we don't know. That's one of the things we're going to be solving for. And ball 2, and by the way, notice I transitioned them, right? So this is after the collision. What direction will ball 2 be going after the collision? To the right. And so again, that's the other final velocity we don't know. Everybody good? Got a little visual going on? If you've been watching curling, this happens every once in a while, right? And so, well, no, never mind, because your target ball stones are at rest. Sorry, I've been watching a lot of Olympics. The gold medal round for the curling was this morning. Did anyone watch it while you got ready for school this morning? I saw YouTube. Oh, okay, yeah. Wait, hold on. US was not in the medal contention for the mixed pairs. Don't give me spoilers for the men's and women's events. Okay. So I won't give all the secrets away, but the mixed doubles curling is over. But anyway, it was pretty neat. So curling, lots of collisions, by the way, but you usually don't have 2 of them moving towards each other because your target ones are stationary. So never mind. Sorry I brought it up. Okay, so here's what's complex about it. Let's attempt to solve this with momentum, because Ms. Earhart says 99% of the time you can do conservation of momentum, right? And so in the beginning, who has momentum? Well, they both do. And so M1 V initial 1 plus M2 V initial 2. After the collision, they're moving independently. And so we have M1 V final 1 plus M2 V final 2. And it's those 2 final velocities that we're going to try and solve for. And so at this point, we need to remind ourselves, hey, they have equal mass. And so even though I designated M1, M2, because y'all, will they always be equal mass? No. So I'm trying to do the setup that's good for many, many problems, not just this one. But with the recognition that M is M, they can all cancel out. And so M goes away. And so we can plug in the two initial velocities. And so 2 plus 3, question mark? Oh, momentum cares about direction. And so that's something I haven't made note of yet. And so if I say to the right is positive, then the one moving to the left needs to be negative. And I could change it. I could go the other way, but you got to take into account direction. And so 2 minus 3 is -1. Now, we're at the point where, oh no, I have two unknowns in one equation. What's complex about this? What are we going to have to do? Say again. A second equation. Two unknowns, two equations. So what's our second equation? Well, if it's elastic, kinetic energy. And so conservation of kinetic energy. And it's a net, since you have more than one. And it's not just in a little bit, whenever we do a ballistic pendulum, you're going to see conservation of mechanical. That's a different situation than conservation of kinetic. This is only true because of that one word they said, elastic. Okay. And so in the beginning, I've got two objects that are both moving. And so we've got the 1/2 m1 v initial squared plus 1/2 m2 and its initial velocity squared. And be careful, subscripts, superscripts. And then afterwards, both are moving independently. And so we'll have two kinetic energies after the collision. And again, I'm doing the setup that's good for tomorrow's elastic collision that doesn't have equal mass, okay? But on this one, since M1 equals M2, what can we do? We can cancel out the masses because it's in every single term. Oh, wait, look, what else can we cancel? The 1/2. Now, don't get cancel happy. Usually you don't cancel more than one. 2 is probably a max. Don't cancel. Oh, the velocities are all squared. Don't do that. And so to finish it out, now remind yourself, kinetic energy and energy is scalar. We really don't have to worry about direction. And even if you did put -3, you're going to square it, right? And so we get that 2 squared plus 3 squared equals, oh, look, it's the same two unknowns, but they are squared. And so I have two equations with the same two unknowns. We're going to solve one. I'm going to solve for momentum, one of the variables with the momentum, and then we can plug it in to the energy statement. Yes? But before we do that, just real quick, what's 4 plus 9? 13. Yeah. Okay, so here we are with these two equations. I'm just going to pick one. It really doesn't matter which one I solve for first. And so let's just isolate. Let's solve for maybe VF1. And so VF1, make a little room here, would equal a -1 minus VF2. And so this expression, we want to plug in to the kinetic energy statement. But wait, the kinetic energy statement squares that expression. Oh no, what F word are we going to have to do? We got to FOIL, okay? And so let's FOIL. And so we would get what? +1 plus 2 VF2 plus VF2 squared. Okay. And this is the squared value of VF1? And so I'm going to slide to the right. 13 equals 1 plus 2 VF2 plus VF2 squared. But don't forget the other VF2 squared. So that's with it substituted in. By the way, not every elastic collision has you do this, okay? It just so happens this is what we got to do with two unknown speeds. Maybe tomorrow it's two unknown masses and you don't have to do foil and quadratic. Uh-oh, quadratic's coming. But before we do quadratic, notice I've got VF2 squared plus VF2 squared, combine like terms and get 2 VF2 squared. Watch your twos, coefficient, subscript, superscript. And I can combine like terms with 13 and 1. I've already said we're going to do quadratic, so let's go on and solve for 0. 1 minus 13, negative 12. And then we bring on down the 2 VF2. And so true story, you can, factor out a 2 or reduce everything by 2. But at the end of the day, this is in quadratic form, A, B, C. And it'll give you 2 answers. So I've already put it in the calculator, sing your song, whatever. It's either positive 2 or negative 3. Now, this isn't like doing quadratic with time where, oh, it's never the negative. This is a velocity. Isn't it possible that it could be negative? And so let's, hold your question just for a second. So let's slide back over to that picture. We solved for VF2. So VF2 should be going what direction at the end? Positive. So we're going to pick the positive answer of 2 meters per second after quadratic. And then how do I find the other, VF1? I plug it back into one of my simpler equations. Hey, don't they add to negative 1? And so if I say, so keep this one going over here, negative 1 equals, well, VF1 is what we want. And this one's 2. It's what? Minus 3. And so we get negative 3 meters per second for the first ball. And you're like, Miss Earhart, you just had us do all that messy algebra when you could have just told us to switch their velocities.
Oh, that makes sense.
But hold on, does that mean every elastic, you just switch their velocities? No, so let's give a big asterisk here. This is a special case. What makes it special? Big masses are equal, and it has to be elastic. They have to say the word elastic, okay? Bouncing off, it could still be inelastic, but if you have an elastic collision with equal masses, they do just trade velocities. Question? Newton's cradle? Yes. And so these are all equal masses, and we said that this is as close to elastic as we totally can. And so, if I was able to move 3 of them out of the way and just do a collision with one, it's actually, that reminds me of the curling. Those are equal stones. And so if you have one at rest, let me set this down and I'll actually try it. Okay, I don't want to tangle, so I'm going to do it nice. Watch, it's still going to tangle. Okay, so 3 are out of the way. I've got 2. And so if I lift one up and the other's at rest, equal mass, they should trade. And so the one I'm touching right now, final velocity should be 0. And whatever initial velocity this one has before the collision should fully transfer to the one initially at rest. And so watch one collision in 3, 2, 1. And that one did come to a stop, okay? And you actually see that in the curling. I saw that one time and I was like, ooh, no angles, head-on collision. It just traded. It was, you know, geek out, cool. Okay. Uh-oh. As long as I don't make it worse. Okay. There we go. Okay. I get real paranoid on the tangling of my Newton's cradles. Question. Okay. Okay.
Whenever we pull it up, did it end up being 1 plus 2 VF2 and then plus
VF squared.
Okay.
Yeah. It was when we combined it with the other VF squared, combined like terms, that it became 2 VF squared. Okay. All right, so complex, because the algebra was messy, right? Okay, and again, it's not that all elastic collisions are messy like that. Now, the one below is one that's not going to be on the quiz. Yes, yesterday or last class, at some point, we did concepts of 2D, right? So maybe you're initially going north, you want to be going west, so that's X and Y. And so the concepts of what's needed to get the result, that's maybe up for grabs, but the math will save, okay? So I'm going to wait on this one. All right, the next one to go through, I've got a simulation. It's a ballistic pendulum, and this is what we'll probably spend the rest of today's class on. And so ballistic pendulum, so this website, I'm going to go in and pull it up. New share. Okay, so this is that website if you want to play with it later. I kept the default masses. I kept everything default. Now I did hide the bullet's initial velocity. This is what we're going to solve for in our first example with a ballistics pendulum. And so by the way, if you don't know ballistics, watch some Mythbusters. They do ballistics all the time. What does it mean? It's the study of firearms, okay? Now, we are not going to do this in person. We'll take our safety first. We'll stick with the simulation, okay? And Mythbusters, safety first is their priority, okay? So as they say, don't try this at home. If you've ever watched Mythbusters, that's their disclaimer at the beginning of every episode. Don't try this at home. We're the professionals. So I'm a professional with this simulation. So here we go. We've got a block of wood. It's attached to 2 strings. And we're going to fire a bullet into that block of wood. Now, based on the picture, that bullet is going to be embedded into the wood. What kind of collision is this? What kind of inelastic? Completely or perfectly inelastic. They stick together at the end. So what's conserved? Momentum is conserved. Is kinetic energy conserved with any inelastic collision? No. But wait, this system is swinging back and forth. We've done that before, Miss Earhart. We've done that in energy when you have a height change. So we are going to do a conservation of mechanical energy after the collision. But during the collision, kinetic energy is not conserved. Are you catching it? Are you hearing it? Don't worry, we'll write it out. So we're about to be on page 7. Here's our given. I'm going to reset. So write this down, page 7. There's some blank space. We're going to use that to solve for the initial velocity. Huh? I'm going to tell you. Our unknown initial velocity of the bullet, VIB, question mark. The mass of the bullet is 0.075 kilograms. 0.075 kilograms. We're solving for the initial velocity of the bullet. The mass of the wooden block, wood will be my subscript, W, is 4 kilograms. And then you might notice on the right-hand side, there's this slide measurement for height. And so I'm going to hit fire again. And so when it's all the way at 0, notice it lines up with the bottom of the block. And I don't know if I said it earlier, but we've got 2 strings. Why 2 strings? You could support it by 1. Well, if you just had 1 string, imagine the block rotating. We're not studying the rotation just yet. So the 2 strings help keep it level. And so from here, I can actually measure. I'm going to let it play a couple times. Does that look good enough? People who can tell?
What?
And so I've lined it up with the maximum height when it's at the top part of the swing. So 0.43 is our max height. That's the data we're collecting. Okay, so let's use that data. I'm going to switch back to 0.43 meters, yes. So I'm waiting on it to switch over. New share, OneNote. Okay, and so what you should have written, mass of the bullet is 0.075 kg. Mass of the wood, I don't want to use block because they're both a B. So later I'll simplify B bullet, W wood, 4 kilograms. We're trying to find the initial velocity of the bullet. Now I didn't say it a while ago, but you saw before the collision, what's the initial velocity of the wood? 0. And then the other measurement we took was that maximum height, 0.43 meters. Okay, and so this picture that kind of lines up right there, there's actually 2 parts to a ballistic pendulum, and this is like classic physics problem, okay? And so I can't guarantee it'll show up on the AP exam, but I think the chances are pretty good. It's classic physics. Notice part 1 is the collision. Now we embed, and so the only thing conserved is going to be momentum. Yes. I'm recording. Okay. Ask me later. And then part 2 is actually the swing after the collision. Now, after the collision's done. Momentum is going to decrease because, well, my velocity is decreasing. So I don't want to use conservation of momentum for the swing, but y'all know height changes. What else is changing? Well, velocity's changing, height's changing, energy's changing, right? And if we neglect air resistance, can't we say that part 2 has a conservation of, watch it, mechanical energy? Kinetic turns into potential, right? During the swing. And so don't think, oh, she's elastic. No. Elastic is conservation of kinetic energy during the collision. That's not true. And so these are always like a 2-parter. And so we're trying to find that initial velocity of the bullet. And so let's start with the collision. And so for part 1, the collision, let's do net momentum before the collision equals the net momentum after. Well, who has momentum before the collision? The bullet, the wood, both? Just the bullet, because the wood isn't moving. And so we've got MB, VIB, and that's what we're looking for right there. Equals who has momentum after the collision? Just the wood?
No, the string.
Not the strings. It's both of them. And aren't they moving together if you're embedded in the wood? And so I'm going to call it, I'm going to take a system approach, right? Or if you want to write MBW, as long as you know it's both of them. And I like taking a system approach because if I'm inside the wood or inside the car, aren't I going the same speed as the car? 60 miles an hour for the car, 60 miles an hour for me. I know I switched examples, but the bullet and the wood are traveling together. They're going to have a common velocity. Everybody good? Okay. And so we start plugging in mass of bullet, 0.075. We're looking for that initial velocity of the bullet equals system or combined mass. Well, it's the bullet plus 4. That was the mass of the wood. And I know I'm showing them separate to prove the point, right? It's a combined mass. And then we have the final velocity after the collision. Wait a second, were we given that? Did we measure that? No. So here's what makes it a two-parter. We got to pause on the collision and we got to transition over to the swing so that I can go find that final velocity. Wait, the final velocity from the collision is the initial velocity of the swing. It's that transition from part 1 to part 2 speed, right? We've done this before. So now for part 2 of the swing, what's true? Well, momentum is not going to be conserved. It's actually going to decrease as it swings higher, right? It slows down. And so we're going to take a look at that conservation of mechanical energy. And this is for the swing. So remember, energy, we're looking at locations. And so initially of the swing, it's the low point. Final, it's the high point. And so at the low point, what kind of mechanical energy does our system have? At your low point, kinetic. And so we've got kinetic energy initially, and it's of the system. This is after the collision. We're already embedded. And it's going to swing up, split second, stop. So where'd all that kinetic energy go? Transferred to potential, gravitational, and we're still together. The bullet, we assume, didn't fall out, so it's still a system. And then we plug in our equations for both. So we get 1/2 mv initial squared, which mass? System. Equals that good old mgh, and this is our max height, which mass? System. And when you really pay attention, it's helpful. What's going to be true about the mass in this statement? It can cancel. Now, true story, we know the masses. Keep them if you want them, but it should cancel in the energy statement. Did it cancel in the momentum statement? No, it wasn't equal mass this time, right? And so we measured the max height. We're trying to solve for that velocity. So we got a 2gh and square root, right? So we plug in 2 times 10. And the max height that we measured was 0.43. So grab a calculator. So remember, this is the initial for the swing. It's equal to the final of the collision. And I hear 2.93. Sounds familiar. Meters per second. Now, technically, this is a speed. Energy gives us a speed. But if we think about the picture, if we go back to the picture, maybe to the right is positive, right? We fire the bullet to the right. It's going to move to the right as it swings upward. And then you just pause. You end the story at the max height. Maybe it never has to come back, yes? And so I'm going to say this is a positive velocity that now we can plug in to the conservation of momentum equation. And so that positive 2.93. Now we should be able to solve for the initial velocity of the bullet. When you calculate, let me know what you get. And then we'll switch back over to the simulation and see. It's the system's velocity at the beginning of the swing, which would be the final of the collision, which is that missing piece that we had earlier. 159.2, I hear. And I hear a second, third, okay. And so 159 might sound high, but remember, it's a bullet, it's okay. And so I'm going to switch back to our simulation. It should keep going, yeah, because I didn't hit pause. So it's still going, physics land, right? It doesn't come to a stop. And so I'll check the box, and it says on the simulation, 160. Close enough? 159.2? Sure. I don't know if they use 9.8 or 10. I don't know with rounding. Was my measurement the best, right? So there's a lot of factors that could make the numbers off. But overall, 160, 159, thumbs up, good to go. Good on Ballistic Pendulum. All right, let me get back to OneNote. Look at the picture below. Are all ballistic pendulums going to be the same? Well, what if the ball, if it's a ball, what if it comes out, right? It doesn't embed, it goes through. Notice maybe that steel marble becomes a projectile, right? And so be careful, there's always something that AP is going to make a change to. And it's about applying all your physics concepts. So I don't really have an example with that one. It was just a different visual. What if the ball comes out? It doesn't stick into the wood. Or what if it's later, page 17, you fire a bullet, it becomes embedded, but then the whole thing goes across a tabletop. Maybe there's friction, maybe there's not, right? And then it flies off. And so just be careful, learn how to apply to different problems. Okay, last one. I think we have time to do it. This was actually an old AP B question, and the setup is very, very similar. We got a block. It's going to have two strings hanging from the ceiling. We're going to fire a bullet. It says it's a 2 kilogram block initially hanging from at rest at the end of a 1 meter string. We got two of them. And then it says a 0.003 kilogram bullet moving horizontally with a speed of 1,000 meters per second. Wow. It strikes the block and becomes embedded. So again, that one word embedded tells us what kind of collision. Inelastic, and if you want to get specific, completely or perfectly inelastic. And so momentum is conserved. Is kinetic energy? No. After the collision, the combination swings upward but does not rotate. Thank goodness. Calculate the speed of the combination just after the collision. And so again, we had height change previous. We used conservation of mechanical energy. Here it's talking about the collision. So what's our game plan? What's our plan A? If it's a collision part, use conservation of momentum. And so that net initial momentum is going to equal the final momentum. In the beginning, it's just the bullet. And so mass of the bullet and its initial velocity. And by the way, it says bullet block. I'm going to pretend that block is made of wood. I'm going to keep the W like the simulation. After the collision, who has momentum? Both together. It's a system, right? And so mass of the system and the final velocity. And that's what we're trying to solve for on this one, the speed after the collision. So VF is what we're solving for. And so this one is just a one step. We have all the other numbers. Mass of bullet, 0.003. Initially moving 1,000. Wow, how convenient. Move the decimal 3 places, right? Okay. And then the system, we got 2 plus 0.003. Not as convenient, but plug it in and let me know what you get. 3 divided by 2.003. 1.5, yeah. meters per second. Now it came out positive. By the way, if you pay attention to vectors, which I didn't address direction, in the beginning, what direction was our bullet going? To the right. Can we make that positive? After the collision, what direction is the system going? To the right. So I got to keep with positive. And so it's kind of already built in, but definitely pay attention to directions with collisions. And so there's your answer for part A. Good? B says, calculate the ratio of kinetic energy of the bullet initially to the kinetic energy of the bullet block combination immediately after. Ratio, what's the equation for ratio? I don't see that on the formula chart. They just gave it to us in the problem. The ratio, so usually it's like 2 to 1 or something, right? It's a ratio, it's a fraction. And so it's the kinetic energy initially of the bullet to the kinetic energy after, and it's of the combination. So I'm going to write system there. And so our answer is going to be like 2 to 1, 3 to 1, whatever it comes out to be. And so, by the way, they'll also ask for like percentages, and it's a ratio times 100, right? To make it a percentage. But here it's just a ratio. And so we have 1/2 mass of bullet times the initial velocity squared divided by 1/2 system mass and the final velocity squared. And if you notice what happens, what could happen, 1/2 can cancel. And so we plug in the mass of the bullet, 0.003. How fast was it going before the collision? 1,000 divided by the system mass, which is, which is divided by the system mass, yes, to answer your question. And then it was going 1.5. Now notice Miss Earhart forgot to square. And I kind of do that on purpose right here because if a student forgets to square, these numbers give you a 1-to-1 ratio. You'd be like 1-to-1. But when you square the velocities, you get, and I'm just for time purposes, I'm going off memory, someone tell me if I'm wrong, 3,000 for the numerator, 4.5 for the denominator. And usually you reduce it to one of them being 1. So this would come out to be like 667 to 1. Okay. You get like 10 decimals. 2 or 3 digits are your rounding kind of sig fig rules on the AP exam. So wow, this one started out with a lot of kinetic energy, 667 times the energy that it ended with. So where did all that energy go that wasn't maintained? No. This is in the collision, right? It's not taking into account the height change. It's just with the collision. What'd you say? Non-conservative forces. So mainly, y'all, heat loss, right? Heat loss. One more little bit, if you'll humor me. One more little bit to finish it out. The height change. And so this is the swing. This is that part 2. This is the conservation of mechanical energy. So at the low point of the swing, we have that system kinetic energy. We're repeating what we did on the sim, right? At the end, when it swings to the high point, we got that MGH, and it's a system mass. What can happen? Cancel the system mass. Now we're going to be solving for the height this time. So divide both sides by G, and it basically becomes VI squared over 2G. Now, which VI? You got to plug in the right number. What VI are we going to do here? It's the 1.5. It's initial to the swing. It's the final of the collision. And so 1.5 squared divided by 20. I think it's like 0.11. Initial velocity. So it's for the swing. So initially you're at the low point to the high point. And so at the low point, this is all after the collision has occurred. Okay. It's that transitional speed. And so 0.11 meters, of course. And next time we'll solve for the angle that the string makes. How about that? A little bit of trig recall. Okay. So tomorrow we'll continue in the packet. Okay.